Good afternoon, Professor, and thank you for being here. We have the pleasure to being interviewing Professor Vidya from Illinois University. She's an experimental physicist working in the field of STM and with an amazing trajectory. Thank you for taking the time to chat with us today.
You're welcome.
We want to know everything we can about you and your career, so let's start from the very, very beginning. Did you ever see yourself doing something else than physics? Well, actually, than science.
I didn't know what I wanted to do when I was an undergrad. I did engineering because, when I was growing up, that's how it was. It was a 4-year engineering program. So by the 4th year, I realized that I was very interested in fundamental questions and not really in, engineering problems. So. Yes, so I learned a few years into my undergrad that I wanted to do science.
Do you believe this metallurgical engineering background conditioned your research line nowadays?
I think that I'm an experimentalist because of my background. Because when I learned engineering, we had to, you wouldn't believe it, we did everything. We did welding, carpentry, smithy, machining, every single thing you can think of. We did all the practical things. So we learned everything. It was quite extensive. So I think that's one of the reasons I decided to become an experimentalist, yes.
And what dragged you exactly to condensed matter physics?
I think, because I knew I was coming from an engineering background and I didn't have a physics background, I didn't want to make it so difficult for myself that it would be I knew there would be a barrier, right? I would have to learn a lot of basic physics. So I picked condensed matter because it was closest to metallurgical engineering in some ways. So I would at least have some background. But also I did a master's and I did it in a group that was a condensed matter group. So that was another reason I picked condensed matter. So it was sort of a series of circumstances, yeah.
Now, I wouldn't dare to say that you're an expert in quantum materials because nobody's an expert in anything nowadays, but working in low-dimensional materials, as you do, obviously make quantum phenomena blossom. Mm-hmm. Could you naively explain to us what a charge density wave is and what mechanisms trigger its operation in low dimensionalities?
So in solids, we have electrons, and of course, we have the atoms, which are mostly the core, which are the protons, and then the electrons surrounding them. The electrons in solid live in these energy eigenstates. And if you look at the charge density, normally without a charge density wave, normally the charge density is uniform if it's a metal. But then you can, in certain circumstances, if you go to low temperatures, it might be energetically favorable for the charge to change such that there's more charge, less charge, more charge, less charge. So it's a spatially inhomogeneous density of charge. And that's called a charge density wave. So it's, and that has lower energy than a uniform charge density. Dimensionality, essentially, you can have a 3D CDW system. You can have a 2-dimensional charge density wave system. Most charge density waves are made because there's strong coupling between the electrons and phonons. Phonons are lattice vibrations. So whenever you have strong coupling like that, you get a charge density wave. Yeah, and and the energy of the system gets lowered.
So in your seminar this morning, related to these charge density waves, you mentioned the formation of phasons that can be, or initially are massless, but can acquire mass. Mm-hmm. In certain materials, especially the ones you work with, could you explain to us what mechanisms give rise to the operation of the mass?
If you want to think about it naively, this is not exact. You can think of mass as resistance to motion, right? And in the kind of excitation that I was talking about today, that is, you take this charge density wave, which is a sort of a change in density periodically, And if you shift it in real space, that's one excitation of the system. And that's what I was talking about. It's a change of the phase of the charge density wave. And for the kinds of CDWs I was talking about, that requires no energy at all to move the CDW here and there. It doesn't cost any energy. But you can imagine that if this charge density, as it's oscillating, it feels some resistance, then that's like acquiring a mass. So that can happen because of these things called Coulomb interactions, which are always there in any system. But if you have lots and lots of electrons, then these Coulomb interactions become very weak. But then if you don't have too many electrons, then the Coulomb interactions can be strong again. And it's that interaction between this charge oscillation and these Coulomb interactions that actually gives a mass. So it's like almost like a resistance to motion. Yeah.
You work with an STM. So this might sound a very naive question to you, but I thought STM was especially implemented for spatial resolution images. How were you able to achieve the time resolution measurements with your STM?
It's a trick, actually. So the way we get time resolution, we couldn't get it with a normal STM. So we do it, the way we get it is by coupling the STM to light. So we have these pulses of light. So there's light that, you have a short time interval for which you have light. So you have light on, light off, light on, light off. So this short time interval is called a pulse. So we have these pulses of laser light. And we can change the time interval between the pulses. And we control the time interval between two pulses. That's what gives us time resolution. So the time resolution doesn't just come from the STM, it actually comes from the laser light.
Yeah. And related to the implementation of a laser, ultrafast laser with an STM, what technical difficulties did you encounter to achieve this?
Many. But I have to say that they were not solved by me, they were solved by my postdoc and my student. But, we had, first, this technique and the way we implemented it, it's new. So nobody has done it the way we did it. So we didn't know if it was going to work in the first place. But we had, every single step we had some issue, and then my postdoc and student found a solution, and then after 2 months there would be another issue. So there was a series of issues, and every time we encountered a problem, they found a solution. So it's just been one thing after another, but it's quite amazing that it works.
The fact that you were able to measure these phasons, was it your first idea to use an STM to measure these phasons? We didn't expect to see what we saw. There are other systems where we've wanted to look for something and we failed for various reasons. So I think we just got lucky. Yeah, we thought we would try, but we didn't know we would succeed. Yeah. I think, and that's how experimental physics works now. So kind of being lucky. Yeah. And also one of the major challenges of being an experimental physicist is dealing with all the data and knowing which of these data is the real result and which one is like noise or background. Regarding your 0.22 terahertz frequency, what challenges did you and your team find to determine this was coming from a charge density wave rather than other fast events on the sample? And yeah, how were you able to track this down?
Yeah, no, it's not. That's one of the biggest problems in any experiment. Like, how do you distinguish between an actual result and an artifact? I think that's why this experiment was so important for us, because in most of the other systems that we've looked at with our laser STM, with our ultrafast STM, what you see is just a very simple decay with some time constant. And to figure out what that means is really hard. So in this particular case, because we saw oscillations and it has this particular very well-defined frequency, and this had been seen before by another technique, that made life a lot easier. It also gave us a lot of confidence in our technique, actually, to tell you the truth. Without this experiment, we wouldn't have had confidence, and now we know we can really measure dynamics at these time scales. So it's because there have been other experiments that have seen the same frequency and the same temperature dependence.
Also, regarding your pump probe STM technique, could you elaborate a bit on that in a more naive way so that our listeners can follow?
Let me think. So I think the best way to understand it is when light hits a system, it creates, everything is excited. Electrons go to higher energy states. And eventually these electrons, they decay to low energy states, and then they create excitations as they're decaying to low energy states. So for example, one of the excitations that they create is this phason that I was talking about. So that's just one pulse of light. It creates all these excitations. But what we do in my technique is we use 2 pulses of light. And we change the time between these 2 pulses. And because each pulse creates an excitation, you can imagine that if the 2 pulses arrive simultaneously, then the kind of excitation they will create will be different from if the 2 pulses are very far away from each other. So that's how we get time resolution, by changing the time delay between the 2 pulses. And so we change the time delay and we measure the current as a function of this time delay. And that's what gives us information on what's happening in the system. Yeah, so the time information is all coming from this time difference between the 2 pulses.
Continuing with the line of working with STM, but now looking ahead to the future, what implementations do you need to do you think that need to be done for an STM to unravel the quantum world? This is a very open question, more of a personal response from you, but
I mean, it's amazing how far we've come, right, in scanning tunneling microscopy from the time it was invented to now. We've been able to see things we never imagined we would see. And you know, I can't predict what's going to happen in the future, but if combining time resolution with spin resolution would be quite interesting, for example. So right now we can only see charge excitations with this probe that we have. But if we can see spin excitations, so things like magnons and so on, that would be really sort of another opportunity. I think we haven't even explored everything that we can do with this ultrafast system, because right now we're using 1 frequency of light, which is close to an EV in energy. We can change the frequency of light and go down to 100 millielectron volts. And so for low frequency light, it can directly excite phonons, of certain kinds of phonons. So I think the phase space of things you can do is quite huge. Yeah, there's a lot to be done.
And also a lot to be discussed with other teammates and groups of expertise. This is also a very interesting question. How do you view the opportunities of interdisciplinary projects regarding this field of expertise?
Yeah, that's a really good question. I think one of the biggest problems we've always had in STM is that our surfaces need to be so pristine because we're so surface sensitive. The other problem we have is that we cannot look at insulators. Our materials need to be conducting. So I think we're trying to overcome at least the second problem, which is the fact that it's hard to look at insulators. There are really new advances that have allowed us, that are allowing people to look at insulators. I think Combining STM with another tool like AFM would be pretty cool. Then you could look at more technologically relevant materials because AFM is able to scan things that STM can't. So if you want to do something more practical, then you might just combine an STM with some other technique. But the STM by itself, it's a little problematic because the sample needs to be flat and clean. And our resolution depends on temperature. So those are huge constraints.
As we approach the end of our interview now, if I may, I want to give it a bit of a personal twist, not just scientific. During your postdoc work, you faced the challenges of combining a very successful science career and the formation of a family. How were you able to keep the balance between both of them? And what advice would you give a young scientist with a similar will or situation?
Yeah. So first I have to say it's always hard to have babies and to have a career. That time period is always difficult, but it is possible, right? That's the most important thing to know. People survive.
It's being done.
And it's being done, right? I had a very supportive husband. That really helped. These days, men are taking on the burden of taking care of children as much as women, which is why I just heard that here you get paternal leave as much as maternal leave, which is really important. If you want men to take on the responsibility of taking care of babies, you have to also give men paternal leave. So that helps a lot. I really think that the only thing I can think of in terms of advice for someone who's thinking of having children and wants to keep their career on track is to get as much as help as possible, in whatever way possible, because you can't do it by yourself. So try to get help. That's all I can say.
It's okay. Rely on someone.
Yeah, rely on whoever is available in whatever way. Don't think you have to do it all by yourself.
Did you ever imagine your position in physics would be such important and fundamental and inspiring for young people, me included?
No. You don't think that that's going to ever happen, and you know, if it's true, then thank you. But for me particularly, I feel like interacting with students is very, very rewarding, and it's the best part of my job. So it's a two-way street.
What challenges do you think young scientists nowadays need to overcome to claim a spot on the top of the field?
This is really a good question. I think that the first thing is you have to really figure out your own interests, and you have to chart your own path. So you have to, figure out what you are good at, and you have to build a career that takes into account your individual strengths. And so don't follow anybody else's career path, is what I'm trying to say. The second is you should have a network of people you can, rely on. You should have collaborators and friends you can call. When we get data that we don't understand, I go and knock on everybody's door in the department and say, do you know what this means? Do you know what this means? So you need to have people you can rely on. That's really important. And then the third thing I would say is that always have some big picture goal of something really cool and interesting that you want to do. Don't get bogged down by the small stuff. Remember that why you wanted to be a scientist in the first place. We are all inspired by the big science and the stuff that we heard that when we were kids. So don't forget that and aspire to do the big science. And even if you're doing the little stuff, which is also really important, have that in the back of your mind. Yeah, that's what I would say.
Thank you. We'll try to keep that light going. So thank you again, Professor, for taking the time to chat with us. It was a pleasure.
Thank you very much.